Thank you very much for joining. That's a great pleasure for me to be part of this exciting event. My name is Makarov. I am from Helmholtz-Zentrum, Dresden-Rossendorf. I will speak about our work on geometrically curved ferro and antiferromagnets, which is considered now as a field of curvilinear magnetism. As you can see, we benefit from a broad network of collaborators where different teams contribute to fundamental understanding of effects of what is happening with geometrically curved magnetics in films, and also technologically oriented community which is working on the realization of flexible, stretchable magnetic field sensors. This is one of the motivations which drives these activities in curvilinear magnetism, where magnetic thin films are prepared as magnetic field sensors on polymeric substrates, which can be geometrically curved. They are very light, still they are very robust and cannot be destroyed even with such kind of very harsh mechanical deformations as you can see here. So you can still prepare high performance magnetic field sensors on such kind of unconventional substrates, which allow you to use them for different types of applications, which are ranging from magnetic electronic skins for human-machine interfaces, for virtual augmented reality applications, where you can use them as high-performance printed magnetic switches for interactive electronics. You can use this flexible high-performance magnetic field sensors also for control of very unique magnetic actuators like magnetic soft robots, or you can use also the similar concepts for biological applications. So basically there are plenty of applications of such kind of curvilinear magnetics in films, and of course the performance of those sensors is determined by local bands, local curvatures which you have in these magnetics in films, and therefore optimization ways for this kind of very special types of magnetic field sensors, you will need of course to understand the change of magnetic responses which you have in such kind of geometrically curved magnetics in films or nanowires. This is exactly my talk about a fundamental aspect of curvilinear magnetism, where we will discuss what is the change in curvilinear antiferromagnets and ferromagnets in terms of gained responses. It is insightful to go back to the work of Yuri Gaididay, where they discussed the anisotropic Heisenberg ferromagnet is a completely local model where you have only exchange and anisotropy energy, and you rewrite the energy functional into curvilinear reference frame, and every term which has spatial derivatives, like for example exchange or magnetostatic, for example, which is not considered here, will be restructured. And for example, exchange will be restructured in a way that you will have not only Heisenberg exchange in the curvilinear reference frame, but you will gain also additional two contributions to the exchange interaction, where one will have a symmetry of sine squared, cosine squared of parametrized magnetization, which is quadratic in curvature, and it behaves as an induced anisotropy response. It means that every curved magnetics in films will gain additional anisotropy response, which is not related to the striction which you have in thin films, but it's imposed by the geometrical transformation. In addition, you will have the term which is linear in curvature, and it has a symmetry which resembles the usual for us inhomogeneous Zaleshinsky-Murray interactions like Lifshitz invariants, which means that any kind of geometrically curved magnetics in film will also have chiral responses, even if this is intrinsically a chiral material. And this of course makes a lot of interest in the community, because you can get chiral responses in standard magnetics in films which you use like cobalt permalloy. In order to understand the impact of this, it's insightful to discuss the one-dimensional system of a heliomagnetic wire, where you will have a heliomagnetic phase transition between homogeneous and periodic state, which is governed by the strengths of Zaleshinsky-Murray interaction, which is an intrinsic property of the material. In case of a curvilinear helical heliomagnetic wire, you will have the possibility to modify the homogeneous state due to the curvature-induced anisotropy, which will result in a tilt of magnetic easy axis away from the tangential direction, and at the same time the heliomagnetic phase transition will now be determined by the vector of so-called mesoscale Zaleshinsky-Murray interaction, which is a vectorial sum of the intrinsic Zaleshinsky-Murray interaction and the extrinsic one, which comes from the geometry, which comes from torsion and curvature of this space curve. If you have a possibility to change the heliomagnetic phase transition by geometry, you can come up very nicely to the possibility to create a memory. For example, if you will think of encoding the 1 and 0 like bits of information into the state where you have periodic and homogeneous magnetic states which have different average magnetization along the axis of this helix, you will be able simply to tune the geometry of the helix to the phase transition, and now crossing the point of the phase transition can be done by a tiny geometrical transformation of this helical wire, which we can do, for example, by embedding it into piezoelectric material or simply sandwiching your helimagnet between the piezoelectric materials. What is important about this, like an added value which you have, it's an artificial magnetoelectric material where magnetic state can be controlled by applying electrical voltage to the piezoelectric matrix. And what is important here, that the change of magnetization is so large that you can get a very large converse magnetoelectric effect in this artificial magnetoelectric material, where you can get a large converse magnetoelectric effect in this material, which is about an order of magnitude larger than what you can get in the best laminates which you have from, let's say, magnetostrictive and piezoelectric materials. Of course, all these predictions are very interesting only if you can confirm that these chiral effects which are coming from, let's say, exchange interaction are real experimental observables. In order to do such kind of verification, Alexei Volkov recently investigated switching of parabolas. So he took the simplest curvilinear geometry which you can imagine. It's a parabola which is not only the simplest geometry, but it's also geometry which has the simplest set of magnetic domain states. For example, you can get magnetization which is simply going along the stripe, or it can point, for example, in one direction. In this case, you will have a domain wall at the apex of this parabola, right? Now, if you will monitor the switching of this parabola in a magnetic field which is applied along the symmetry axis of the parabola, you will be able to observe two switching fields. In the second switching field at about minus 50 millitesla, it's a field which is due to the magnetostatic, like its shape anisotropy, it's expelling the domain wall from the system and reversing the system. And the first step is actually something which is very interesting. The first step does not exist in a stripe which is not geometrically curved. And this is parabola out of permalloy. As you can see, it's not a very small parabola. You have 2 micrometer long stripe, 200 nanometer wide stripe, and 10 nanometer thick. It's a symmetric stack. You don't have any type of Zoloshinsky-Murray interaction which comes from interfaces of this parabola. You can now combine the theoretical, like analytical, simulations analysis, and also experiments in order to understand what is the nature of this first switching field, which you can see here at about, let's say, 20, 30, 40 millitesla. In this case, you can analyze this field as a function of curvature at the apex of the parabola, and you will see that this field scales linearly with curvature, which is exactly something which you would expect from the curvature-induced Zoloshinsky-Murray interaction, which comes from the restructuring of exchange interaction due to the curvature in the system. Now you can use again the theories which are available in the community in order to relate this switching field which you measure experimentally with the strengths of this curvature-induced Zoloshinsky-Murray interaction. It's an effective chiral interaction which you have in this 10 nanometer thick parabola due to the curvature gradient at the apex of the parabola. What you can see here, it's a blue point, it's experimental data which corresponds very nicely with theoretical analysis. And what is interesting about it, it's the strength of this Zoloshinsky-Murray interaction which you can get in the system, which is about, let's say, in the order of 1 millijoule per square meter. And this is something which is comparable to the well-optimized asymmetric cobalt-based sandwiches which you use, for example, in order to create Skyrmions or Skyrmion bubbles in such kind of extended asymmetric cobalt sandwiches in films. This you can get in 10 nanometer thick permalloy, which is curved to the geometrical parameters which are easily achievable in experiment. When you know that this effect of curvature-induced chiral interactions which are coming from the exchange are real experimental observables, you can of course think about which are striking the demonstrations of these effects. For example, if you will extend the system from, let's say, quasi one-dimensional parabola to a simplest curved two-dimensional object, or three-dimensional in this case, where you will have a plate-like geometry with let's say, two bands, you will obviously expect to have a pinion of magnetic domain walls exactly at these bands. You have in this geometry two bands, you will have two domain walls which can be supported in the system, or zero domain walls or two domain walls. And in this case you will have different states which are ground state, for example, homogeneously magnetized, or the one which will have only one domain state, which will be a Skyrmion state, or with two domain walls where you will have Skyrmionium states with different topological numbers. And what is important, that these domain walls are also chiral because of curvature-induced Dzeloshensky-Marie interaction. And what is important, that now you can manipulate the size of this Skyrmion not by the geometrical, not by the intrinsic properties of this thin film which you use for this investigation, but by the geometry. So you can make a smaller Skyrmion, you can make a larger radius Skyrmion simply by playing with the radius of these band regions in the system. You can go one step further and you can, for example, reduce the central region, the flat central region, into the basically point. You will transform your plate-like geometry to, let's say, Gaussian geometry. And this system is very special because you will have the possibility to create the external, the larger domain wall, which is pinned at the band, which we discussed before. This is some kind of Skyrmion bubble, if you want. At the apex of the Gaussian bump, you will be able to create a Skyrmion of a very small radii. It's a curvature-induced Skyrmion due to the Dzeloshensky-Marie interaction, so it has all properties of the standard Skyrmions which you have in the chiral materials, like you know it from asymmetric cobalt sandwiches. And what is interesting about this curved system is that the energetic of these Skyrmion bubbles, which you can create in array of these Gaussian bumps, is such that you will have the ground state, which is actually the Skyrmion lattice, right? In this case, due to the interplay between geometrical curvature, you will have the possibility to tune the system, the chiral interaction which comes from geometry and anisotropic interaction which comes from geometry, in a way to make this as a ground state. And now you can investigate the properties and parameters of this Skyrmion lattice in the ferromagnet, where the Skyrmion lattice is a ground state, which is not possible in the extended thin films without corrugations, where the ground state is of course homogeneous state, and Skyrmions are only excitations. So you have a very interesting playground for ferromagnets with such corrugations. Of course, you can imagine that there are a lot of activities on the experimental community to work on the realization of such kind of curved objects, where you can use nanopore templates, perforations, the deposition of curvature templates prepared by spherical particles, by ion beam structuring, where you can really nicely tune the exchange coupling between the neighboring cap structures. So you can really expect very soon the experimental confirmations of all these exciting effects with localized Skyrmions in curvilinear geometries. I'm very much looking forward to these investigations. Everything what we discussed before was about local interactions. So everything what was induced by geometry, it was effects which came from the spatial derivative of the exchange interaction. Of course, what makes magnetism very exciting, where you have domain walls, for example, domains in your system, it's micromagnetism, where you consider also magnetostatic interaction, where non-local effects also come into play. So everything what we discussed before, like this parabola, pinion of domain walls at the parabola, Skyrmions and Skyrmionium states, for this you need to have only the approximation where energy terms only up to the first linear term in thickness are considered. As soon as you will make a next step, which was done recently by Dennis Shecker, you will necessarily get non-local interactions in the system, and those interactions are, of course, very complex to analyze, but they bring very interesting physics in your system. In order to understand this physics, I would like to start with a very classical discussion which is introduced about 50 years ago by Brown in micromagnetics, where he introduced the concept of surface and volume magnetostatic charges in order to describe what is happening in the thin film, for example. If you have a thin film with equal interfaces at the top and at the bottom, the interaction between surface and volume charges is allowed, but it's trivial, so it's basically canceling out, and this energy terms does not give any contribution to the energy functional. What will happen in the curved thin films, because you have loss of symmetry because of curvature, Denis Sheka proposed to use the language of covariant derivatives to describe the physics in this material, and in order to better understand what is happening due to non-local interactions, he introduced the concept of three magnetostatic charges, where the conventional volume magnetostatic charge is now split into tangential charge and the geometrical charge. The geometrical charge depends on the mean curvature and on the normal component of magnetization. So basically you need a texture which has out-of-plane component of magnetization, that this magnetostatic charge is actually active. In this case, you can write the non-local interaction in your system in a way that you will have not only standard surface and tangential charges interacting with each other, but also you will have additional interaction between surface and tangential charge and volume, tangential and geometrical charge, which cause very interesting chiral symmetry break in the system. I would like to come back to exactly this classical diagram where you have local and non-local interactions and what you can get out of them in terms of anisotropy and chiral interaction. And what is interesting that from local interactions you have obviously anisotropy and also Dzyalushinsky-Moria interactions from spin-orbit coupling, for example. Non-local interactions usually give you effects which are like anisotropy effects. What is interesting in curvilinear thin films, that these non-existing chiral effects from non-local interactions become possible to be observed. And this is a very interesting aspect which is given by curve geometries for magnetism community, where you can have a really energy degeneracy lifted for, let's say, different types of domain walls which are pinned, for example, in this elliptical tube at the neck of such kind of tube. So that's an interesting prediction. Where does it come from? So if you will analyze this non-local part of the magnetostatic energy, you will see such kind of two terms which can support chiral symmetry breaking. So this is an interaction between surface and tangential charges and geometric and tangential charges, which can allow you to observe the non-local chiral symmetry break. And we were able to derive only sufficient conditions, which, for example, considers the symmetry of the geometry, the symmetry of the texture, and also the different parity of the texture with respect to the reflection, like mirror planes. And in this case, you can at least predict that or another system will have the chiral symmetry break due to this non-local interaction, which comes from magnetostatics, but not from let's say, standard spin-orbit interactions which you have in the system. Now, with this theory which you have curvilinear micromagnetism, you can classify different interactions like chiral local, chiral non-local, anisotropic interactions which you can get from geometry, and the impact on the magnetic textures, on domain walls, on the ground state which you can have, or even on magnetization dynamics which you have in thin film which is geometrically curved to different shell as a different surface as it's shown here. So if you want to analyze what is happening, you can make a very interesting exercise and have a look on this table and just try to guess what kind of effect will your texture become chiral by curving, for example, your out-of-plane magnetized thin films in a tubular geometry. Of course, it's not only ferromagnets which are interesting in magnetism. There are a lot of effects which people consider in antiferromagnets, and this is, of course, stimulated development of the field of curvilinear antiferromagnetism. What can the curve geometry bring for the antiferromagnets? In this case, Alexander Polipovsky made a transition from spin lattice model of a very simplistic case where you have achiral, isotropic, one-dimensional antiferromagnetic spin chain with a dipole-dipole interaction. In this case, you can transform the spin lattice model into micromagnetic model, where you will have from dipole-dipole interaction hard axis anisotropy along tangential direction, and you will have the terms which we already discussed before in exchange energy, which are anisotropy, which comes from restructuring the exchange, and Dzyalushinsky-Moria interaction. As soon as you have Dzyalushinsky-Moria interaction in the system, this and anisotropy, it makes your achiral isotropic antiferromagnet behave as a chiral biaxial helimagnet with a geometry-driven phase transition, helimagnetic phase transition between periodic and homogeneous states. You can nicely investigate those types of effects and impact of geometry on this phase transition. You can analyze what is happening, for example, with the linear excitations on the background of, for example, homogeneous state. Here you have unexpected effects emerging. For example, you can get for acoustic branch of spin waves, you can get possibility to have such kind of a minima with a negative group velocity on the dispersion curve, which allows you to investigate also a collective interaction of magnons in exactly this minima of the dispersion curve, maybe even speculating about Bose-Einstein condensation in K-space, which is actually an interesting playground which is enabled by this very simple antiferromagnetic spin chains. Antiferromagnets are very rich because they have, compared to ferromagnets, because they have many sublattices. In this case, you can have very interesting effects coming from exchange and also from anisotropy. For example, if you will have inter-ion or single-ion anisotropies, you will be able also to formulate the model beyond the sigma model which we discussed now, and in this case exchange will become a little bit more complex. You will have not only terms which are proportional to n prime squared, where n in this case it's a nihil vector and m it's a vector of ferromagnetism. You can see that vector of ferromagnetism enters the energy and starts determining the properties of the systems, and you have a very interesting term where n prime and vector of ferromagnetism m are coupled together with a coefficient which is a parity breaking coefficient. Parity breaking term enters the energy functional of the system, and it determines homogeneous DMI and weak ferromagnetism. And this is exactly something which I would like to discuss very briefly here. You can write also for the same model what we discussed before, one-dimensional antiferromagnetic spin chain with a dipole-dipole interaction, whether you have hard axis anisotropy parallel to the tangential direction. In this case, you will be able to get also terms which are proportional to this WD type of term, where you have a homogeneous DMI hidden there. This HD, it's a Dzyalushinsky field which is related to the homogeneous Dzyalushinsky-Mourier interaction. As you can see from the symmetry, this term is proportional to curvature, so basically it can be observed even in the flat curved curves, and at the same time you need a special symmetry of the nihil vector, where you need at least a normal and or tangential component of nihil vector to be non-zero to be able to observe this effect. This can be easily realized in homogeneous ground state of an antiferromagnetic helix, where you have obviously curvature, so the coefficient of homogeneous Dzyalushinsky is not zero, and also you have proper ingredients in nihil vector, which allows you to get also this homogeneous Dzyalushinsky-Mourier interaction, which is responsible for anisotropic responses and eventually can cause weak ferromagnetism in a system. As you can see, this effect is not very strong in a homogeneous system, where you will have maximum, typically it's in the order of 0.1% up to 10% of anisotropy field, but you can enhance it in a one-dimensional system substantially, like orders of magnitude, simply by having a system where you will have also a domain wall. What is interesting about one-dimensional antiferromagnets is that this system supports the non-zero magnetization at the location of the domain wall. And this makes the term in the anisotropy, this omega d, substantial. You have not only Dzyalushinsky field, homogeneous Dzyalushinsky field, but also magnetization non-zero, which makes this term active in the energy functional. And in this case, you can magnify, for example, orders of magnitude the homogeneous Dzyalushinsky field at the location of the domain wall, and makes it impact very, very significant on the behavior of the system. Now, if we will consider this parity breaking term in an energy functional, you will see that it enters also anisotropy, and you can drag it all theoretically into the understanding that the system where the spins are oriented along the space curve, so three-dimensional curve where you will have torsion and curvature, can support weak ferromagnetism, or it can be a weak ferromagnetism where, for example, magnetization will be determined by, of course, curvature and torsion in the system, and it can be sufficiently strong. Now, what is the difference between the curvilinear and ferro and curvilinear antiferromagnets? This is briefly shown here, that you have different effects which you can have coming from exchange and anisotropy in the system. For example, if you will want to have a homogeneous Dzyalushinsky-Mourier interaction, you will need to get back to the anisotropy in curvilinear antiferromagnet, and this cannot be obtained in ferromagnets at all. From exchange, this term does not appear. At the same time, if you will have inhomogeneous DMI, like the Lushinsky-Morier interaction, intrinsic one, this you can get from exchange interaction both in ferromagnet and antiferromagnet, but not from anisotropy and things like this. So basically, by analyzing this table, you can really see the differences which you can have in curvilinear ferro and antiferromagnets. Now, if you will have effects which we discuss always were because of local geometrical curvatures. Of course, in the system, real system, experimental system, you have also boundary effects. And these effects are also significant that substantially modify the properties of magnetic ground state and also excited states like domain walls and Skyrmions, for example. This you can simply show even on a prototypical collinear antiferromagnet like chromium oxide, where you will have a single crystal with such kind of topographic patterns like mesa patterned here. And you will see that the domain wall, when it interacts with this mesa, is interestingly modified. For example, it can be pinned, it can be deformed. As you can see, you can have a very special S-shaped curve in this material. Because of this pinning, the pinning can be so strong that you can even get possibility to speculate about possibility to create a memory concept based on domain walls in such kind of patterned antiferromagnetic materials. So boundaries definitely affect the properties of those systems. You can analyze what would be the effects of boundaries on G-type chiral antiferromagnet. Again, you can formulate a transition from spin lattice to micromagnetic models. You can derive properly the boundary conditions here. And you can see that as soon as a domain wall comes to the boundary, it gets deformed. It gets, for example, such kind of twist. It gets broadening, for example. And this is happening at a relatively large distances. So in principle, if you want to have a bulk-like properties of domain walls, you will need to have your system at least of 5 to 10 exchange lengths wide. Otherwise, the modification of the texture due to the boundary effects will be substantial, that you will not have a bulk-like properties. The same is valid for Skyrmion. So this is a slab of G-type chiral antiferromagnet where you can support the formation or stabilization of an antiferromagnetic Skyrmion. And again, the same story applied. As soon as you are far away from the top and bottom surfaces, you will have bulk-like properties of this, for example, Bloch Skyrmion. But as soon as you approach the surface, you will have, for example, the broadening of the Skyrmion, the radius will change, the phase of the Skyrmion will change, it will become mixed Bloch-Niel Skyrmion and will be substantially modified. Again, the characteristic length scale where the modification happens is in the range of couple of exchange lengths, like 5 to 10 exchange lengths. This is also something like a design rule for the experimental community, which will need to take care that the thickness of the sample is sufficient in order to have at least kind of a bulk-like behavior of this antiferromagnetic Skyrmions. Otherwise, the expectation what you see from theory and from experiment will be actually pretty much different. All right, instead of summary, I would like to come back to this slide which I showed at the very beginning, where we analyze the impact of curvature on magnetic shell or ferromagnetic shell in this specific case, where you can see that geometry can cause additional anisotropy and chiral responses in the system. In this case, you can tell that you can use curvilinear magnetism as a platform to design chiral and anisotropic magnetic responses in the system by tailoring the geometry of thin film. And this is simply complementary to the standard material screening approach which we use in the magnetic community to design chiral responses, for example. It's a new approach to material science which you can now start exploring for fundamental investigations, but also for different types of applications of magnetic field sensors. Thank you very much for your attention. I am very much open to any questions which you might have. Please feel free to get in touch with me. We are very open to collaborations. Thank you very much. That's an overview slide again. In case you have questions, I am very happy to discuss with you. Thank you.